Hello students, let us talk today about symmetry elements and symmetry operations within group theory. It is one of the important topics of group theory. So let us try to understand it with the help of certain natural things like flower, crystal, butterflies. If I consider flower and butterfly, most of them have very symmetrical structure. That means if you try to consider them in different orientations, their configurations within space at different angles are indistinguishable with respect to each other. That means they have certain symmetrical elements. However, there are certain things like crystal or say certain optically active molecules which do not have symmetrical elements. Now, say for example, I want to perform any symmetrical operation on a particular molecule. Then I can perform that symmetrical operation with across an axis, around a point or through a plane. That means I have three types of basic symmetry elements, that is symmetrical axis, center of symmetry and the mirror plane or the reflection plane. Here I have specified one point symmetry. Now what is this point symmetry? If there is a point in a space that remains unchanged under all of the symmetrical operations which you are performing, then the resultant symmetry is referred to as point symmetry. It means whenever you consider any molecule and you perform any one of the symmetry operation on that molecule, and during that operation there would be at least one point within a molecule which will not be altered, it won't change its own position, and such symmetrical operations will be considered as a point symmetry. Clear? Now let us talk about the symmetrical operations. There are 5 different types of symmetry operations which generally exist. One is identity specified by E, then is the proper rotation specified by Cn, then is center of symmetry or center of inversion given as Ci, then is plane of reflection or the mirror plane specified by sigma, and the last one, the improper rotation specified by Sn. Today in this video, I'll discuss with you about 2 symmetrical operations, the first 2, identity and proper rotational axis, that is Cn axis of rotation. Now when I say identity, what is this identity? As we know, it is specified by E. This is basically the molecule itself, its own identity, the configuration of that molecule itself. Then the case is why it is important. See, in case of identity, it might appear to us that it is unimportant, but it is included for mathematical completeness, and some useful relationships can be established with the help of the symmetry operation identity. So it is as such an important operation applicable in mathematical concepts. So we'll now concentrate on the second type of symmetry operation, that is proper rotational axis. It's also called as n-fold rotational axis of symmetry. In this case, we are rotating the molecule by 360 degree upon n times or 360 degree upon n rotation. Now what is this n, or what is this n specified in Cn? So I can say this n is the number of times I have to rotate my molecule, right, through a particular angle. Say for example, if I say I want to perform the C2 axis of rotation, that means here my n is 2. It becomes 360 degree divided by 2, that is 180 degree. That means for applying the C2 axis of rotation, I am rotating my molecule by 180 degree each time. And the condition whenever I apply the symmetry operation is that whenever I apply a symmetry operation, the molecule which is obtained after performing that operation should have a same configuration as the original one. That we can understand by taking this example of trans N2F2, that is trans orientation of dinitrogen difluoride. To make it more clear to you, I have specified this fluorine atoms through subscripts A and B. Now in this case, let us consider an axis of rotation passing through the center of the molecule, and this axis of rotation is parallel to the plane of the paper. If I rotate this axis through 180 degree, then I'll be getting this particular configuration. But in this configuration, as we can see, the fluorine atom, which we were expecting to be at the top right of the corner, top right corner, is now been shifted to the other side. Similarly, this particular fluorine atom is been shifted to the other side in the configuration. So I'm not getting the original configuration back as the original one, right? So I can say C2 axis of rotation does not exist when it is kept parallel to the plane of the paper in case of this example. However, I am taking now a C2 axis which is perpendicular to the plane of the paper. That means I am passing C2 axis of rotation in this direction, passing through the center of the molecule. Now through this axis, if I am rotating it by 180 degree, I am getting this configuration. So what you can observe in this configuration, the fluorine atoms are at their same positions. The subscripts you can observe, they are changed, and that is very definite, that is very certain. When you are rotating it, we are getting this axis of rotation, rotating it by 180 degree, then this fluorine will take this position and this particular fluorine will take this position. But however, the configuration remains unchanged, and now in that sense I can say that here when C2 axis is perpendicular to the plane of paper, then C2 axis of rotation exists. Now let us take another example. The same molecule we are taking, but now in its cis form. So cis dinitrogen difluoride. In this case, again I am taking a C2 axis of rotation passing through the center of the molecule, and it is parallel to the plane of the paper. As we can see, when I rotate it by this axis, then this fluorine will interchange their positions. However, the configuration of the newly formed molecule will be same as that of the original configuration. So here in this case I can say that C2 axis of rotation exists when it is parallel to the plane of the paper. Let us take a next example of platinum tetrachloride, PTCl4. In this platinum tetrachloride, there are two types of proper axis of rotation which can exist. The first type is C4 axis of rotation. When I say C4 axis, that means 360 divided by 4, that is by 90 degrees. So I am rotating the molecule by 90 degrees each time. So let us consider that the C4 axis of rotation is perpendicular to the plane of paper passing through the platinum atom. So when we are rotating this C4 axis of rotation by 90 degrees, then I have specified here A, B, C, D. So when we are rotating it by 90 degree, what will happen? Each of the atom will move by 90 degree angle. So this A chlorine will come by 90 degree orientation on the next side, and that this way you can get this particular configuration. Again we can observe when I am performing the C4 axis of rotation, the configuration remains unchanged. It will appear to us in the similar way as the original one. So there is C4 axis of rotation in this case. The other possibility to this is C2 axis of rotation. Now there are 4 C2 axis of rotation in this particular molecule as specified in the figure. So 2 across the diagonals and 1 passing vertically through the center and the other passing horizontally through the center. So we have 4 C2 axis, and whenever you rotate the C2 axis of symmetry, you can get, when you rotate it by 180 degrees, say for instance here, this chlorine atoms will move on this side, this chlorine atoms will move on this side. So it is applicable to all the C2 axis, the 4 C2 axis which exist in this case. We are going to get every time the original configuration back, and so this C2 axis of rotation exists for this, for platinum tetrachloride. Let us take the next example of ferrocin. What is ferrocin? Ferrocin is a sandwich compound of Fe, iron atom. So we have two forms of this. One is the staggered ferrocin and the other is eclipsed ferrocin. What is the basic difference between both of them? In case of staggered ferrocin, the vertices are facing opposite to each other, and in case of eclipsed ferrocin, the vertices are coinciding with each other, and so that we can say both the pentagonal rings are exactly parallel to each other within the molecule. So this is the side view of the molecule which has been given to you, and this is the top view of this ferrocene structures. So as we can see in case of eclipsed, both the rings are coinciding and so they have common vertices. However, to make it clear to you, I have given it with the two colored sketch pens so that you can understand that one ring, the rear ring, and the other, the front ring, both are coinciding, having similar vertices, same vertices, coinciding with each other. However, in case of staggered ferrocene, the vertices are not coinciding with each other, and that we can observe it, see it in this particular figure. Now, how many rotational axes exist in this case? There are basically again two types of rotational axes. One is C5 and other is C2 axis in both the cases. When I say C5 axis, that means 360 divided by 5, that becomes 72 degree. So in this case, I am rotating it by 72 degree. So let us imagine an axis passing through the center of that molecule, passing through the Fe as well, which is in the center exactly. So that has been shown in the form of a point in this particular view of the ferrocene molecule. Similarly, here it has been shown. So when I am taking this axis passing through this molecule from the center and rotating it by 72 degrees, what will happen in the case of staggered ferrocene? The rear ring will be rotating by 72 degree. Similarly, the front ring will be rotating by 72 degree, and the vertices will be shifting their position. So this one will come here, then back wala, this one will come here, and so on. But however, the configuration, the original configuration will remain unaltered. You will observe that it is having an indistinguishable configuration when we are performing a C5 operation. It is applicable to staggered ferrocene. The same thing is applicable to eclipsed ferrocene. So we are having C5 axis of rotation in both the cases. The other possibility, C2 axis of rotation. In C2 axis of rotation, so you have to just a trick you can consider here to find out how many C2 axis of rotation exist in a particular molecule. You have to just consider the center of that molecule and try to divide that molecule into equal halves. So if I am taking this molecule divided into equal halves, I can find out when I rotate through this axis by 180 degree, I am getting the same configuration back. Similarly, if I am taking this C2 axis and rotating the molecule by 180 degree, I will be getting the same configuration back. In this way, there are 5 different positions through which I can pass this C2 axis. So in total, staggered ferrocene has 5 C2 axes of rotation. Similarly, in case of eclipsed ferrocene, again I have plotted 3 C2 axes in this case. So start from the vertex and try to cut that axis on the opposite side. So we are having this one C2 axis shown here. This is C2, second one. This is the third vertex crossing through here. Then you can plot it from fourth here, and then from fifth you can plot here. So again we have 5 C2 axes in this case as well. That means in general what you can say, in both the cases we have 1 C5 axis and 5 C2 axis. Let us come on the next example, that is alene. Now what is this alene? Alene is basically a cumulative diene. Cumulative diene, that means it is a type of conjugated polyene. So here we are taking an example of a typical alene whereby there is a central carbon atom attached to 2 adjacent carbon atoms with double bonds. So the hydrogen atoms in case of alene, here these are in the plane of the paper. The terminal hydrogen atom here is below the plane of the paper, and this hydrogen atom is above the plane of the paper. Now let us try to perform C4 axis of rotation in this case. C4 axis means rotation by 90 degree. So if I am taking this axis of rotation passing through this center, this way, passing through the complete molecule, then and rotating it by 90 degree, then I am getting this particular configuration that you can observe yourself. So what is going to happen? This in plane hydrogen atom, when you are rotating by 90 degree, it will move above the plane and the other one will move below the plane of the paper. So we are getting this configuration. So accordingly, now what we can observe here is that plane of the paper hydrogen atoms which we are expecting, now they have changed their positions, right? And here these positions are being changed and they have been converted into plane of the paper orientation. So this configuration is not similar to that of the original one. So I can say in this case C4 axis of rotation does not exist. Now let us see which axis of rotation can exist in this case. Let us take an example for C2 axis of rotation. So to make you more clear, I have tried to plot a three-dimensional figure here in case of allene. So in three-dimensional space, I have the C1, C2, C3 carbon atoms attached here, arranged here, right? And these are the 4 hydrogen atoms. So this terminal in plane hydrogen atoms are this H1 and H2. And the above plane and below plane hydrogen atoms, this is the above one, H3, and the below the plane of the paper, it is H4. Now, if I take a C2 axis of rotation coinciding through all the 3 carbon atoms, rotate this by 180 degree, this particular axis, what is going to happen? What can you observe? The H1 position, H1 hydrogen atom will move to this position, to H2, H2 will come to H1, H3 will move to H4 and H4 will move to H3. So what about the configuration you are going to achieve? Same as the original one, right? So I can say C2 axis of rotation exists in this case, and rather it is a principal axis of rotation. I'd like to specify here what do you mean by a principal axis of rotation. You can find out which is the principal axis of rotation. First you have to check whether it is of highest order or not. Say for example, I take this example of platinum tetrachloride. There were 2 axes here, C4 axis and C2 axis of rotation. So C4, n is equal to 4, it is greater than this, n is equal to 2. So larger is the n value, that means larger is the order of the rotation, that will be considered as the principal axis of rotation. So C4 is the principal axis in this case. Now which is the principal axis in this case? Here it is C2 axis of rotation. Why? That we can understand. So you have to consider if there is no difference in the order of rotational axis, then you will check through how many atoms that particular axis is passing. So here it is passing through 3 atoms of the molecule. So it's the highest order rotational axis. So it will be considered as the principal axis of rotation. In addition, there are 2 more C2 axis of rotation in this case, which are perpendicular to this C2 axis of rotation. One is passing through the central carbon atom, this one specified as C2 prime, and the other is the axis of rotation which is passing in this direction. This is again other C2 prime axis of rotation. I'll try to make you understand how this C2 prime axis of rotation can exist. So try to assume this axis of rotation and move it by 180 degree rotation. So what is going to happen? H1 will take the position of, first it will move by 90 degree here, then 180 degree H3. So H1 will take the position of H3. Where will your H2 move? H2 will take the position of H4 when you move by 180 degree. Then where will H3 wala atom go? H3 will come and take the position of H1 when you move by 180 degree, and H4 will come and take the position of H2 after moving by 180 degrees. Similarly, you can observe for C2 prime as well, right? So I hope you're clear with your concepts regarding the first 2 symmetry operations. The other remaining symmetry operations I'll be continuing in my next video. Till then, study hard, take care.